What's up, everybody? Hope you're having a good day. Today, we are going to be hacking on the Arlo Q security camera from Netgear. Why are we going to take a look at this device? Well, they have recently reneged on a commitment that they made to their customers, and people aren't happy. That commitment is actually written right on the box of this Arlo certified refurbished camera that I recently made the purchase of. Let me read that commitment for you. 7 days of free cloud recordings. Arlo comes with recurring 7-day free cloud recordings. Live stream or view recorded video and audio for up to 7 days. So, the basic premise is that they committed to their customers. They say you buy upfront, you pay an upfront cost for this camera, and we are going to provide you with a basic level of service that gives you 7 days of cloud recordings of clip uploads to the cloud that you can go and then view those recordings. And they are reneging on that promise, and the reasoning for it is pretty interesting, and that's what we're going to dive into today on this channel. If you're not familiar with what we do on this channel, we do hardware hacking. We take devices like this apart and try to find security vulnerabilities or jailbreaks to devices such as these IoT devices. But how did I hear about this? Well, let's look over here. So, very popular YouTuber Louis Rossmann brought this to the attention of the community. If you're not familiar with his work, I highly suggest you go and subscribe to his YouTube channel and you check out the work that he does. So Louis Rossmann, he is primarily a Apple laptop repair professional, and on the side has taken up an interest in advocating for the right to repair. Now, this is not going to be a video diving into the full philosophy of the right to repair movement. I suggest you go listen to his videos to get the full background there. But this issue that he's bringing up is somewhat of an ancillary. It's related, but not exactly the same as the right to repair issue, but more in line with the issue of planned obsolescence with manufacturers of these electronic devices having a business model such that they need you to throw this device away every 1 to 2 years and buy a new one in order for them to make a profit. And so he raises some of the issues with these business models and the promises that were not kept here by Arlo. So let's go ahead and take a look actually at the press release that he discusses in his video here directly on the Arlo webpage. So we can see here on the Arlo webpage that they are announcing that a number of products, not just this device, but this is included on the list, the Arlo Q. We can see here that there's actually a number of devices that are being announced to end of life, and then specifically a number of services. And this is what has made people the most angry, is the removal of the free 7-day rolling cloud storage, right? And Louis notes in his video that this was probably a bad business model in the first place, right? To charge people a one-time cost for a product and then to provide them a indefinite service into the future that has a cost associated with it, right? If you know anything about running cloud infrastructure in AWS, Azure, Google Cloud Compute, storage is not free, right? And so committing to this 7 days of free cloud storage indefinitely into the future is probably a bad business move, but they did it. They made that promise to their customers, and so it's pretty disappointing when they let them down in that way. But why are we talking about this on a hardware security channel? Well, that is a good question. That is because Arlo, partially to justify why they are end-of-lifing support for this camera and a number of other cameras, they claim that it is for, it's right here, data security and data privacy reasons. So that is quite relevant to this channel, what we discuss. Like I said, I am not an expert in right to repair legislation and the repair movement and third-party repair of devices such as these. But my background is in IoT security and cybersecurity in general. And I also have experience working on the product development side of these embedded systems. So I've got a good amount of experience that we can bring to bear on this reason. And we can analyze whether or not this is a legitimate reason for them to end of life a device like this. So first, before we dig into this and look over at the desk on the device that I have taken apart, one of the first things I do as a security researcher, if I'm taking a look at a device, I always want to look and see if anyone has gone before me, if there's any public research that is already available on the product I'm looking at. And in this case, there is some relevant research that this YouTube channel that I want to call out, Flashback team, performed on the Arlo Q+. Now, there is that noted difference between those two devices, and I think we can I've actually been able to determine at least one of the differences between those two products here. You'll see an SD card slot right here on this device, and when we go over to the desk, we'll actually see that that's missing. But other than that, these two devices seem to be the same, right? So it's where they made one similar PCB, everything like that, and they just removed an SD card, or maybe there's a worse camera on the non-Plus model. But most of their research is probably going to have some application to what I'm looking at in my device. And so these researchers did some really cool stuff. They found a special debug mode if you hold down a certain button, and I'm going to show you what that translates into on the device and the firmware version that we have on the device over on the desk. But just wanted to call out Flashback team. They did some great analysis on this product, and they also identified right here, you can see these 4 pins, and they identified that as a debug console, so that will print out the output of the Linux console on this device. So that is also very important. But that's all the pre-research that we want to look at today. Now we're going to go and look at this device on the desk. So you can see here, it's kind of a mess. I've ripped this camera apart with a little bit of finesse and a little bit of brute force, but we have our Arlo Q camera here taken apart on the desk, and you can see that I've got a mess of wires here, and we're going to look at that under the microscope where these wires are connecting to on the board. But I want to show you the wide angle first to show you that this is a USB to serial or USB to UART adapter. And I have 3 wires plugged into it, and then those wires are then soldered to these little tiny black wires that are connected to the board. So a UART is a common hardware level protocol that communicates data, serial data, and can transmit and receive data. So we can see here I've got a black wire that's going to be connected to ground, and then I have orange and yellow. These are our TX and RX. So one of these is going to be to transmit data from the computer to the device, and then the other one is to receive data that's being transmitted by the device back to the computer. And we'll be able to see that in a terminal when we boot this device up. So this device is powered over micro USB here, and then let's jump under the microscope and let's take a little closer look at this device and some of the interesting things that we see on this PCB. So the first thing that catches my eye is this Amberella chip on the board. I do have some experience with this specific SoC. This is an ARM-based CPU and also on silicon here. The reason why I recognize this on a video device is because this is going to not only have an ARM CPU on this piece of silicon, but it also has hardware video encoding capabilities on it, which makes sense because we found this chip on a video device. The other thing that we have right next door to that is our memory. This is our RAM on the system. And then over here, which was behind this shield that, if I can find some tweezers, I will kind of peel this back momentarily. So here is the wireless SoC on this system. So this is a Wi-Fi only based camera. There's no Ethernet port on the back of it. So Wi-Fi is the mechanism that it uses to connect to the internet. And so that is our Wi-Fi chip. And then I'm going to actually unplug the USB so I can flip this over momentarily. And we can see the flash storage here on the back. So this is a 48-pin NAND flash chip. And I've read off and written down the the model number of this flash chip. And I've confirmed that my flash reader will read this chip. So in a future video, what we're going to do is we're going to extract the firmware contents of this chip by desoldering it with hot air and some flux and pulling this chip off of the board, reading it, and then reattaching it to the PCB so that we can continue to have the camera function correctly, but that we can have that firmware dump to do further security analysis of this device. And then I want to show you over here, this is what we're focusing on today. So I'm going to try to zoom and focus in for you here. So you can see I've got 3 wires connected up to this place where there's 4 through-hole through-hole terminals here. And so this is where that UART serial debug console is located on the device. So potentially in a development version of this PCB, they might have actually had like pins sitting in here that a nice little connector could plug into, but they usually remove those during the production runs of the PCBs when they make those. But I've just put these 3 wires in here. I believe it is ground, TX, and RX. These are TX and RX. I might have mixed those up. And then this is connected to ground. And then this other one here is the voltage line, which you don't need to connect to for our purposes today. So, with that in mind, I'm going to just show you back out on my desk cam for a second. So, I've got my micro USB cord here. So I'm going to keep this side unplugged for now, and I'm just going to prepare this by plugging in to our device, so I don't have to fiddle with that side when I want to turn my device on and off. Now the other important part of this device is I'm going to find the buttons. So on this side of the device, we can see these 2 buttons here. One here, and this is the reset, and then this one is called the sync button. Now, the Flashback team, what they discovered is that you could get additional capabilities over the serial console if when you boot, you hold this sync button in. And so I'm going to have, in one hand, I'm going to have this, and then I'm going to be holding the sync button with the other hand, and then I'm going to be basically plugging this into my computer really quickly, and then I'm going to be jumping over to my keyboard and hitting the enter key to pause the boot of this system. So that's what we're going to do right now. We're going to come back over to our screen, and I'm going to bring up our terminal. So here you can see this command that I'm about to execute in Linux. This is picocom. It is a terminal emulator that is going to allow us to connect to the serial connection that UART to USB adapter is going to create on our Linux system. So I'm going to be plugging this in to my computer, and then I'm going to. So first, what we're going to do is I'm not going to press the button, and we'll observe what happens. So I'm holding the Enter key down, and the boot process did not stop. It continued. So that's what we're going to notice is different when we go and hold down the sync key. But actually, let's first go and look at what we see at the first bit of output here. So I'm seeing something right up front here called amboot. So on an Ambarella based system, with that we looked at that CPU, it actually has a special bootloader called amboot. It's not your typical U-boot bootloader. This is a proprietary bootloader. So we don't necessarily have source code to this. So we're just going to be kind of analyzing this bootloader to see if we can get into its menu. And if we encounter any problems. Just a little foreshadowing there. So now, and you'll notice when I hit enter, I'm not, it is taking my input, but I'm not getting a shell or a login prompt out of it, which often you can get from one of these interfaces. So there's some kind of, protections in place there. But let's see what happens when I unplug the device. I hold down that sync key now, and I'm going to plug in, and I'm going to hold down the enter key. I must have hit the... You know what? I think I got the key, those mixed up. Let's try that again. Hold it in. Hey, there we go. So now we've paused the normal boot process of this device, and we hit this menu. So we get some cool ASCII art that says we're in the amboot bootloader. And we get even more information about, amboot, Ambarella, copyright, 2004, 2007. Okay, so yeah, it's a little bit of an older, at least the Linux build or this SDK, this bootloader, a little bit older. We get some information about some other stuff that I don't really care about right now. And then we get an interesting prompt. It says enter 6 to 64 ASCII char keys. So what is this? Okay, I can type some characters into it. Oh, interesting. I hit backspace and it keeps going the other way. So and then if I type something and then I hit enter, it says SHA-256 result, and then it prints out this hex value, which if you're familiar with the SHA-256 hash algorithm, that is pretty clearly a SHA-256 hash. So now the question is this bootloader password? It's clearly it's trying to prompt for a password to actually give us access to the bootloader menu. So what I'm going to do is I'm going to try to figure out if this is a salted or an unsalted hash when it's comparing the password. So if you're unfamiliar with the way that password hashing usually works, it's typically a bad idea to store in plain text the password on a system. This is a bad idea because then if you get access to the memory of that system, the storage of that system, you could just pull the password off, right? So typically what you do is you use a hash function. So let's say I've got the password hello123, right? So I've got this password hello123, and I'm going to send it to the SHA-256 sum program. So there you go. You get this output. So it's a hash function is just something that takes in a variable amount of input. It'll take in any amount of input and turn it into a fixed length output. And so that is really helpful for storing a version of a password that's not the clear text password, right? So now instead of storing this hello123 password, a system can store this hash, and then when the user provides the password, it will conduct that same hash algorithm and then see if they are the same. And if they're the same, then you know that that user has entered the correct password, even though you haven't stored the plain text version of the password on your system. Now, I mentioned salting. What's a salt? Well, people have realized that you can do brute force attacks on these hashes really fast if all you're using is the hash algorithm itself. So oftentimes, to avoid the ability to pre-compute these lookup tables to accelerate password cracking, what oftentimes people will do is they will always append some piece of data. So they'll take the password and then they'll append some random value. We're just gonna call it salt. And so every time that password is entered, it will take the password and it will concatenate onto the end of it some fixed value that is then stored alongside the password hash. And then you get a different result from that hash than you would have if you just hashed only the password, but rather than the password and the salt together. So if we want to figure out if this bootloader is using a salt, what we could do is we could just enter in a known password. We get to pick what we enter for the password, and it tells us the result. See, that in and of itself is terrible, right? They're telling me what the hash of the current password is, and it's allowing me to reverse engineer what's going on because it's giving me this output. It doesn't need to tell me what the result of my password hash is when I enter it. It just needs to tell me if I get to log in or don't, right? But the system gives me this extra information that I can use to figure out what's going on here. So I'm going to type in the password, all lowercase, and I'm gonna hit enter. And I'm going to then similarly hash that password on my system. Now, if you're not familiar with why I am doing this -n-e, that's because if I don't do that, and I take this password, and I'm gonna pipe this password, the password, to a command line hex editor, XXD. And you'll see here that it actually puts a new line character. It appends that onto the end of it. And so I don't want that new line character to go into the hash function that I'm going to do up here. So that's why I do this -n-e. It's gonna get rid of that new line character from what we're echoing in. So I'm gonna say password, I'm gonna send it, and we have a match. So we can see that here, when we entered the password, we got this hash. And it perfectly matches a SHA-256 sum of the text password. So we have now confirmed that this is an unsalted password hash that is happening on this system, which means that we could use rainbow tables. It's a lookup table method of performing password cracking. We could do dictionary attacks on this password, but I don't have the password hash yet. So it's outputting a hash, but it's outputting the hash of whatever I type into this system. So in order to get the password hash, we are going to have to pull that flash chip off. We're going to have to pull the flash chip off the board and go look around in the memory space where the bootloader is stored, where any of the bootloader's data is stored on that flash chip. And we're going to have to find this data so that then we can take that and we can go conduct a brute force attack, an offline brute force attack of this password. So this is just the start of my analysis of this device. So far, my impressions are mixed. So there is some security on this bootloader of this hardware, right? And so are these claims legitimate, right? So when Arlo makes these claims, let's go back over here to their end of life announcement. When Arlo makes these types of claims that they need to, for data security and data privacy reasons, they need to end of life a device like this. Or similarly, when other companies, like this is a point that Louis Rossmann makes, when companies say you shouldn't be able to repair your own device because if we give you the tools to do that, then hackers, the bad guys, could use those tools to also get into your systems, right? There's a couple problems with those arguments, but I want to stick to just the analysis of this device today. We'll deal with some of those other arguments later in further videos. But today, I want to say that my impressions are mixed of this device. Why is that? So there in that console, does it need to be like shooting the the hash of whatever password I enter in out so that I can reverse engineer that? No, not really. Also, it's an older system, but that system has the capability of receiving updates, right? It's not like they can't push updates to it. My impression is that they probably don't want to, right? It probably gets harder to support older systems like that, and there's also a potential in the IoT world that Arlo, that Netgear, that they themselves are not doing all the firmware development, that they are using a third party overseas to do that firmware development. And that can cause complications. Now you can manage that. You as a company can manage that relationship and select a vendor that is going to provide continuous support, continuous security updates, new product features in their firmwares. But maybe they picked wrong, right? And so maybe they're dealing with the logical consequences of having that development capability not under their own roof as a company. These are all good questions, and they're things that we might be able to dig into, and we might be able to get clues as we start to extract the firmware out of this device and take a look at it. So please subscribe to the channel, because there's going to be new videos rolling out on this Arlo device. If you have an Arlo device and if you bought that based on the commitment that they made to you, I'm sorry, and please comment below and tell me if you'd be interested in a project idea that I have. So one thing we do on this channel is obviously the security analysis of this device, but part and parcel with that is the jailbreaking community that exists out on the internets, right? And so there's a potential that, okay, they're going to not allow these clip uploads to their backend. Could we reverse engineer that clip upload process and have it upload a clip to a server that you control so you could continue to get that clip data? That's a possibility. I don't know how much engineering work would have to happen. Reverse engineering and engineering work would have to happen to make that possible. But please share this video and reach out if you're interested in working on a project like that. Thank you and have a great day.